All right, so last time we solved equations that had one step between the problem and the solution. And as the title implies, today we're going to have equations that have two steps. And we're going to add some inequalities in there because why the heck not? All right, so let's go ahead and solve one. If I'm given the problem, x divided by 2 plus 5 equals 11. So this is example 1. We're going to jump right into it. Well, what would x have to be in order for x over 2 plus 5 to equal 11? So you could figure this out. You could use your fingers, think, kind of visualize tokens in your head. You could actually pull out some like manipulatives and figure it out. But we're going to do it by solving, which means get x all by itself on one side of the equal sign, everything else on the other side. So we know, and we're pretty good at solving one step, we know that if I want to move this 5 to the other side, I would just put negative 5 over here and cross this out, right? Because all I'm doing is putting the opposite of 5 on both sides of the equation. And if I wanted to move this 2 to the other side, all I would have to do is multiply a 2 to both sides, because this is a divided 2, and the inverse operation for multiplication is division, or the opposite operation is division. So multiplication, division, addition, subtraction. But I have a dilemma because I have two things I have to do, and I may or may not have to do it in a certain order. Okay, I've sort of answered my question already, because if algebra is anything, it's about order. And we already have order of operations, right? We have PEMDAS that we can work with. So when we're simplifying, we use PEMDAS, right? We do the parentheses first, then we do the exponents, then we do multiplication, division, and then we do addition, subtraction. That's simplifying. But when we solve, and I moved that arrow because I want to actually point to solve. When we solve, we work in the opposite order. So when I look at 2, which is connected to x by division, and 5, which is connected to x by addition, PEMDAS backwards says I have to do the addition subtraction first. So I'm going to go and move the 5 first, and the addition property of equality says that if I put the opposite of 5 on one side, it disappears it on the other side. And now I have to simplify before I keep going. So I have x over 2 left on this side, equals 11 take away 5 is 6. Now I have no more addition subtraction. I can move on to multiplication division, and the multiplication property of equity says that if I do the inverse operation of divide by 2, which happens to be multiply by 2 to both sides, it'll disappear it on this side. By the way, this process that I use is called transposition. Of elements, but just transposition method. So when I say transpose, and I'll say that a lot, when I say transpose, because at some point I want to quit explaining this to you because you're going to get it, I'll just say transpose the 2, which means use the inverse operation to move it to the other side. Okay, so let's go on. So I'm left with an x on this side, and 6 times 2 is 12. Now I have to, at least in the beginning, I really have to check my problems, make that a habit. So I'm going to go back to the original problem. I'm going to put 12 in. 12 divided by 2 plus 5. And I'm not sure if that equals 11 or not, but I'm going to simplify the left-hand side to see. So 12 divided by 2 is 6 plus 5 equals 11. 6 plus 5, 11 equals 11. Yes, I got the right answer, so I can move on. How much fun was that? So I'm just going to do a bunch of examples because I just want to keep having that much fun. So example number 2, 5b minus 7b equals 4. Okay, what do I have here? Let's see. I have a 5 and a 7. Uh-oh. Mayday, Mayday, Will Robinson. So look at this. I have something on this side that can actually be combined. I can do a PEMDAS down on one side of this equation, and I always should. You should always simplify both sides first. So some of us like to put a line down our equal sign. I don't really mind if you do. You'll lose it at some point in the game anyway. But And the line is sort of a clue. Make sure that this side is completely simplified, and it is, and then make sure that this side is completely simplified. So 5b minus 7b is negative 2b. Okay, now both the sides are simplified. Now I can PEMDAS up. I don't have any addition subtraction, so all I have to move is that negative 2. I'm going to use transposition. Negative 2 is connected to b by multiplication, so I'm going to turn it into division. I'm going to transpose the negative 2 from multiplication to division and then finish up my problem. So 4 divided by negative 2 is negative 2. I'm going to check it in the original. So 5 times negative 2 minus 7 times negative 2 equals 4. 5 times negative 2, oh, and we don't know if it equals 4. 5 times negative 2 is negative 10 plus, because negative and a negative is a positive, 7 times 2 is 14 equals 4. Negative 10 plus 14 is 4 equals 4. I'm correct. Well, that was just about as much fun as a barrel full of monkeys. Let's do some more. Example 4. Negative 1 equals z over 3 minus 7. All right, so the next thing I'm going to show you, this is my own personal quirk, and some of you guys it'll help, some of you guys won't care. I'm just going to show it to you because when I do it, I want you to know what I'm doing, all right? I like my variable on the left-hand side of the equal sign. It's just a personal little thing for me. So before I start a problem like this, I just switch the two sides, and you can certainly do that because they equal each other. If they equal each other in one direction, they equal each other in the other direction. So I'm just going to rewrite z over 3 minus 7 equals negative 1. So I've got the same problem, I just put my variable on the left-hand side. So now I'm going to go ahead and solve it. I'll use the line for a little while just because I think it gives a clearer picture of what we're doing. Simplify this side, done. Simplify this side, done. I could find a common denominator, and sometimes you'll see that as a better choice, but in this case it's not really a better choice, so don't do it. I want to get rid of a negative 7 and a 3. Which one do I move first? Well, negative 7 is connected by addition subtraction, which is the bottom of PEMDAS. So I'm going to transpose negative 7. When I do that, the opposite of negative 7 is a plus 7, and it's going to disappear from this side. So I'm left with a z over 3 equals negative 1 plus 7 equals 6. Okay, done. Now, my z is still not alone, though, so I'm going to move or transpose this 3. 3 is connected to the z by division. The transposition of division, or the opposite of division, is multiplication, which makes it disappear on this side. Clean it up. Z equals 18. Okay, now we have to check. So 18, trading 18 for z, over 3 minus 7 equals negative 1. I'm not sure if that's true, I'm checking. 18 divided by 3 is 6, minus 7 equals negative 1. Negative 1 equals negative 1. Done. All right, so let's do one last example before we move on to inequalities, and it'll be a problem with words. So the output of a function is 7 more than 2 times the input. Oof. Seven more than 2 times the input. We want to solve for whatever value. We want to solve the equation. So this one is a little bit different in the sense that it says the output and the input. So this has to do of a function. So when we're talking about functions, we're talking about equations that have 2 variables in them. So in this case, we have the output is the y variable and the input is the x variable. So now we're looking at the y of an equation or a function is 7 more than 2 times the x. We can totally write that, right? So we're going to say the y of a function is, well, this is my equals sign, and so y goes on this side, and then all of this goes on the other side. 7 more than 2 times the input. Well, 2 times the input would be 2x, and 7 more than that would be plus 7. And the rest of the instructions that I saved, so I could do this first, is to write an equation and then find an input, or find the input whenever the output is 15, when y equals 15. So let's go ahead and do that. So that's simple. This has two variables in it, but it's going to do the same rules that we're going to do exactly the same thing we've already done. In this case, I'm going to write 2x plus 7 equals, well, y is 15. And notice what I did. I put my variable on the left-hand side because that's where I liked it. And now I'm going to solve it the old-fashioned way. I'm going to move the 7 first by transposition. Becomes a negative 7. 2x equals 15, take away 7 is 8. And then I'm going to move the x by the 2 by transposition. A multiplied 2 becomes a divided 2. So x equals 4. And then, of course, I have to check my solution to make sure it's true. So 2 times 4 plus 7 equals 15. Is that true? Well, that's 8 plus 7 equals 15. I can already see it's true, but I'm going to go all the way. And 15 equals 15, so that is a correct answer. Okay, so as promised, we're going to do some inequalities now. And we've already written some inequalities when we converted from words to sentences, much like the previous problem. But we're going to solve some inequalities now that are just given to you. So example 4, this would have been example 5, by the way. So example 6. X over 4 is less than 5. X over 4 is less than 5. This is exactly the same as equal to 5, except that your comparison isn't that two sides of the equation are equal to each other, it's that one is less than the other. And so all of the rules for equations still apply, but you have to keep that inequality consistent. So you still have to do, if you do one thing to one side, you have to do the same thing to the other side. You just remember that you're dealing with an inequality rather than an equal sign. So let's solve this one. 4 is in the way of x being alone, and 4 is connected to x by division, so I'm going to transpose it into multiplication. And so x values have to be less than 5 times 4 is 20. So in order for x divided by 4 for this side to be smaller than 5, guaranteed to be smaller than 5, then I'm only allowed to choose x values that are smaller than 20. All right, so let's check it. Turns out that checking these are a little bit tricky. So we start with a graph. So just a number line graph. And we know 20 is our boundary. So numbers bigger than 20 are not in our solution, right? Not in our solution, because we need x values, our solution values, to be less than 20. So it's all of these numbers that are less than 20, and let me make that really dark. So all of these x values will make this statement true, except notice at 20, I have to decide, is 20 included or not included? And if 20 is included, then I would just color a dot and it would be a solution. But 20 is not included because it's strictly less than, not equal to. X values have to be less than 20. They're not allowed to equal 20, so I'm going to put an open dot. That means when I check this, I have to choose one of the values below 20. So let's choose 19. Oh, let's not. Let's choose 16 because it divides by 4. Is 16 less than 20? Yes, it is. 16 divided by 4. Less than 5? I don't know. Well, 16 divided by 4 is 4. Less than 5? It is. And so we're only going to check one point. We're just going to make sure we have the right interval. Let's do another one. Let's do y divided by 7 is greater than or equal to negative 4. All right, so let's see. I'm going to solve this the same way. 7 is connected to y by division, so I'm going to transpose that to a multiplied 7, and I get y is greater than or equal to negative 4 times 7 is negative 28. So now my number line, negative 28 is what I'm looking at. And I need all the y values that are bigger than negative 28. So that's going to be all of these, because all the numbers that are bigger than negative 28 are on the right-hand side of negative 28. And then I have to ask, is 28 part of the set or not part of the set? And in fact, because it says greater than or equal to, then 28 is included, so I'm going to color in that dot. So all the numbers that make this true are on this region. I could choose 0. 0 divided by 7 is 0. Is 0 bigger than or equal to negative 4? Yes, it is. I could choose all of them or any of them. Let's check this one by just checking the boundary. So let's say negative 28 divided by 7 is greater than or equal to negative 4. Is this true? Negative 28 divided by 7 is negative 4. Greater than or equal to negative 4. Is negative 4 greater than or equal to negative 4? Well, sure, because it's equal to. So that is a true statement. Okay, so there is a special rule for inequalities. Special rule. If anybody wants me to explain this to them in great detail, you're welcome to come and see me on your off time, but this is a rule that the explanation has very little clarity in it. It's just a true statement, best to memorize it. Later you have opportunities to see cases where the rule applies, but at this stage of the game, it's one of those algebra rules I'm just going to ask you to memorize and trust. So the special rule is that whenever you multiply or divide, because remember multiplication and division are the same thing, an inequality by a negative number, switch the sign. So let's do a couple of those examples. I always forget my example when I scroll down. So x divided by negative 4 is greater than 12. So this is an inequality, and I have a negative value. So I might have to switch the sign on this. I won't really know until I get a little bit farther. So I'm going to transpose negative 4 by turning division into multiplication. And look what just happened. I turned multiplication and division. I turned division into multiplication, which means I have to apply the rule. So x is less than 12 times negative 4, which is negative 48. And if I graphed that solution, I would start at negative 48, and I would say that x values have to be less than negative 48, which means they're all these values instead of just one. So with an equality, you get an equal value. You get just one. But with an inequality, you get everything that is less than 48 in this case. And it's not equal to, so I have to put a big open circle for 48. So that's the solution set. And then when I want to check one, just to make sure I've got the right region, I'm going to choose, let's see, negative 48 divided by negative 4. Oh, I'm not going to choose negative 48 because it's not included. So let's choose negative something that divides by 4. How about something bigger than negative 48 that also divides by 4? 4 times, let's take negative 10, or excuse me, negative 100. That's easy enough. Is less than negative 48. So I chose negative 100, which is way over here. Right? So negative 100 divided by 4, two negatives makes a positive in division. 100 divided by 4 is 25, less than negative 48. Whoa, what did I do? Aha! Notice what I did. I didn't put it back in the original problem. So the original problem is x is greater than. I jumped the gun a little bit. So x divided by negative 4, in this case I chose negative 100 divided by negative 4, is greater than 12. Okay, I bet you caught that when I did it. Two negatives makes a positive. 100 divided by 4 is 25, greater than 12. Is that true? Of course that's true. So I know by choosing negative 100, I end up with a true statement in my original function. One more. I know it's getting a little bit long, but big concepts today. Let's take negative 6n less than 24. Okay, so I'm going to transpose negative 6 from a multiplied 6 into a divided 6. So from a multiplied negative 6 into a divided negative 6. If I do that, multiplication division says I have to change the direction of the sign. So I end up with n is greater than 24 divided by negative 6. Negative, positive and negative makes it negative. 24 divided by 6 is negative 4. My solution set, it's a set of numbers because it's an inequality, is at negative 4. N values are all bigger than negative 4. So I'm going to do this. And then it's not included. It's not equal to negative 4. So I can't ever choose negative 4. But I could choose negative 3.9999, right? I can get as close as possible to 4, but I can't ever get negative 4. And then let's check it. So I'm going to plug in negative. I'm just going to write down the original problem to save myself the same mistake I made over here. And make sure that all the white part is what I wrote. Negative 6 times n is less than 24. Good. Now I have to choose a value to plug in for n just to test to see that I'm correct. I can't choose negative 4, so how about if I choose negative 3? That's closer to 0, right? So negative 6 times negative 3 is less than 24. We don't know if that's true. Negative times a negative is a positive. 6 times 3 is 18, less than 24. And by golly, 18 is less than 24, so that's the correct answer. So we've covered a lot of ground. Let's go back and do a quick review of it. It started off kind of simple, started off seeming like it was going to be hard because it was a two-step equation, but we discovered we just work in reverse order to do exactly the same thing we've been doing, and then check our answers. Then we can do the same thing when we take what we've been doing since the beginning of the year, working on turning number or word sentences into number sentences, and we were certainly able to solve that kind of an equation. And then we talked about a special rule for inequalities. So inequalities solve in exactly the same way equalities do, except you have a special rule when you multiply and divide by a negative number. Adding and subtracting by negative numbers, no big deal. But multiplying and dividing with negative numbers, all you have to do is switch the direction of the sign, and that your answers for an inequality is going to be a whole range of values. Rather than just one particular answer, you're going to get a whole bunch of answers that are either less than or greater than some value. And then you have to ask yourself, is the value you got in your equation included or not included in the set?